All right, let's tackle page 2. So page 2, you guys, looks a lot like that last problem in page 1, but we're going to go ahead and go through each problem, so if you have questions, you can have a look, see if you can follow along. All right, so for number 3, we have a 0.851 mole sample of alcohol, and for the purposes of this, you guys, we're just going to go ahead and call this alcohol ethene, which is, in terms of chemical formula, C2H6O. So we're just going to say C2H6O, and we're going to do that rather than having to write out the word alcohol every time. I know it's, that's just what I like to do. So it's burned in the presence of oxygen in a calorimeter. So you have 150 grams of water in the calorimeter, and that temperature rises from an initial temperature, so there's my TI right here, to a high temperature of 81.6 degrees Celsius, so that's going to be my TF right there. So what we're trying to figure out is what is the delta H of combustion of the alcohol. So we're trying to find the delta H for the alcohol, or our ethene, our C2H60. Okay. Now, in order to do that, you guys, we're going to go through that process. We have to start by finding the Q of water. So we're given this data on water. There's 150 grams of water in the calorimeter. It's got a temperature initially of 22.8. We burn the alcohol in the presence of oxygen, and the temperature of that water raises up to 81.6 degrees Celsius. So again, you guys, just a quick reminder that Q equals the mass of my substance times that change in temperature times the specific heat of my substance. And we're going to take a second and go over here and calculate our delta T, or our change in temperature, which is, again, our final temperature minus our initial temperature. So we determined that our final temperature was 81.6 degrees Celsius, and we're going to subtract that from 22.8 degrees Celsius. And if we plug that into our fabulous calculator, we're going to say 81.6 minus 22.8. And so we have a temperature change. Our temperature rises 58.8 degrees Celsius. So when I'm figuring out my Q, and again, you guys, this is my Q for water. So I've got my mass of water, which is 150.00 grams, times my change in temperature, which we determined was 58.8 degrees Celsius, and that's a positive because that temperature rose. And my last value is my, again, you guys, my specific heat of water is 4.18 joules over grams degrees Celsius. So that's what's going to go right here, 4.18 joules over grams degrees Celsius. And once I do the math on that, I end up with a quantity, or Q, of my water. And if I go ahead and just put that in my calculator real quick, I have 150 times 58.8 times 4.18. And that gives me a value, a Q. And again, you guys, I'm going to go ahead and put down that it's positive 36,867.6 joules. And again, you guys, the reason that unit is joules is because joules is a unit of energy, and in my formula I can cancel out my grams and I can cancel out my temperature units, and I'm left with joules. Alright, so what that means is that the water is my surroundings. Okay, when I burn that alcohol in the presence of oxygen within the calorimeter, what that means is that the water is going to absorb 36,867.6 joules of energy, which means that my Q for the alcohol, the C2H6O, is going to be the opposite of that, which means this is giving energy to the water, which means I'm going to have a negative 36,867.6 joules of energy is going to be lost by that alcohol. Okay? So, when it comes to calculating, because again, you guys, we have to try and calculate the delta H of that alcohol, we're going to go ahead and calculate that delta H. And remember, the delta H of that C2H6O is going to be a negative 36,867.6 joules over the moles of that alcohol. And if I look, it tells me right here, I'm dealing with a 0.851 moles of that C2H. Oops, I did that wrong. Yeah, C2H6O. So then when I do the math on that, I'm going to take 36,867. And remember, oh, that's right, 0.6. And remember, I'm going to make that negative, so then I got to hit my little negative button down here at the bottom right there. Divided by 0.851 leaves us with a delta H of negative 43,333 point. And again, you guys, I'm going to round that up to 0.68, so 20, oops, I did that wrong. 43,322.68. Gotta make sure I did that right. For some reason, I got different numbers when I did this previously. Double check all that here in a second. 0.51. I'll deal with that in just a minute. And that's going to be joules over grams. I'm sorry, that's joules over moles. Okay. And if I made a mistake there, my apologies. It happens. So is this reaction endothermic or exothermic? Well, again, you guys, because we're dealing with delta H, and because it's negative, this means that this is going to be exothermic. So this change right here in enthalpy is going to be exothermic, which means that my alcohol is giving energy to the water. Okay, so the water is absorbing the energy, and that's why that temperature is going up. It's the alcohol that's giving away energy, that exothermic reaction, to the water, and that's why the water is allowed to heat up. Okay? And like I said, if I did my numbers wrong, if I'm off, I'm not off by very much, so there you go. All right, let's go ahead and do number 4. So number 4, you start out with if 65.05 grams of water, that's going to be important, that's your mass of your water, is added to a calorimeter at an initial temperature, look, initial temperature, so I can just put TI right there, of 21.2 degrees Celsius, and it's warmed to a final temperature of 24.7 degrees Celsius, so that's going to be my TF right there. When 0.22 moles of NaOH is added, what is the delta H, or the enthalpy in joules per mole of the, and that's sodium hydroxide specifically, okay? So again, you guys, like anything, we're going to start by, again, we're trying to find the Q of water to start with, because water, you guys, again, is going to be my surroundings. We're adding this material to the water, and something is going to change, okay? So I'm going to start by going ahead and figuring out my change in temperature, because like always, I have to figure out my Q of water first. So my change in temperature is, again, my final temperature minus my initial temperature. In this case, my final temperature is 24.7 degrees Celsius minus, excuse me, my initial temperature of 21.2 degrees Celsius. And if I do that, I would take 24.7 minus 21.2, and I end up with a quantity or a temperature gain of 3.5 degrees Celsius. Give me 1 second, you guys. I'm going to grab a sip of water. All right, so we end up with a temperature change of, and that's a positive 3.5 degrees Celsius. So now I have the information I need to calculate my Q for water. I've got the mass of water right there, 65.05 grams of H2O. And I'm going to multiply that by this quantity right here, a temperature change of 3.5 degrees Celsius. And I'm going to be using my specific heat for water yet again. There it is, 4.18. So 4.18 joules over grams degrees Celsius. That's my unit for specific heat. And once I figure that out, and again, I'll go ahead and crank that in there for you calculator-wise. So I've got 65.05 grams times 3.5 times 4.18 equals a quantity of 951.68. And again, you guys, my unit's going to be joules because I can cancel out grams, and I can cancel out degrees Celsius. And again, that is a unit of energy, is joules. Now again, you guys, this is my Q for water, but remember, what that means is that, and this is a positive number, it means my water is gaining 951.68 joules of energy, and specifically it's gaining that energy from my sodium hydroxide. So that means my Q for sodium hydroxide, so NaOH, has to be the opposite of this. If the water got 951 or gained 951.68 joules from the sodium hydroxide, it means that that sodium hydroxide lost 951.68 joules of energy, specifically heat energy. So this becomes the Q that we are going to use to calculate our delta H for my sodium hydroxide, my NaOH. So to calculate that, that means I need to take the Q of my NaOH, so Q of NaOH, over the number of moles of NaOH, and I'm given that during my problem. So my delta H for my NaOH equals my Q, which is negative 951.68 joules, over, according to my problem, I'm dealing with this quantity right here, 0.22 moles. 0.22 moles. So then my delta H for my NaOH, actually let's just put delta H equals, I'll go ahead and do my work here. I've got 900, so that way you can see it. I've got 951.68. And again, you guys, that's a negative, so I have to use this little key down here at the bottom, divided by 0.22 equals a change in energy of minus, actually I'll just put it up here, minus 4,325.82 joules per mole of NaOH, otherwise known as sodium hydroxide. So that's going to be my change in enthalpy right there. So is this reaction endothermic or exothermic? Well, again, you guys, anytime I'm dealing with a negative delta H or a negative enthalpy, it means my reaction is going to be exothermic. And specifically, you guys, when I'm asking what's endothermic or exothermic, it's what's happening in this substance right here. So when the NaOH gets put in the water, we start to see this is breaking up. Okay, this is breaking up, and that energy that is getting released into the surrounding water. And so we see the temperature of the water rise. The water is getting the energy from the NaOH, and the NaOH is experiencing an exothermic process right now. Okay? All right, cool. All right, last one. We have a calorimeter filled with 1,250.0 grams of aqueous, that's an important word, acetic acid. All right? Acetic acid has a formula I can't remember the formula for acetic acid. No. Yeah, I'll come back to it. I can't remember what it is. But we'll just go acetic acid for right now. At an initial temperature of 23.7 degrees Celsius, so 23, that's going to be my TI right there. when 0.1433 moles of NaHCO3 is added, the temperature drops to 18.84. So this is going to be my TF right there. And again, you guys, I want to know the delta H in joules per mole of the substance right here, the what is that? I can't think of what that polyatomic is. We'll just call it NaHCO3. So we have to go through that process again of finding our Q. And again, you guys, I'm dealing with aqueous acetic acid, which means I'm essentially finding the Q of water, because this is an aqueous solution. So my Q for my acetic acid, I'm annoyed with myself because I can't remember the formula for acetic acid. I'll just have to let it go. I'll just put acetic acid right here. We'll go a little AA right there. Yay, acetic acid. And again, we have to calculate that formula. So we're going to need the mass, we're going to need the change in temperature, we're going to need the specific heat of water, because this is an aqueous solution. So let's start real quick by just getting our change in temperature that we experience. So again, my change in temperature equals the TF, which is my final temperature, minus TI, which is my initial or starting temperature. So I figured out that my TF right here is 18.4 degrees Celsius. And I'm going to subtract that from my starting temperature, which is 23.7 degrees Celsius. So my change in temperature, let's go ahead and do some math on that there. I've got 18.4 minus 23.7 equals negative 5.3 degrees Celsius, which means the temperature of my solution, my aqueous acetic acid, dropped 5.3 degrees when we added this substance right here. Alright, so let's go ahead and figure this out. So again, Q equals the mass of my substance, so 1,250.0 grams of aqueous acetic acid times its change in temperature, which was a negative 5.3 degrees Celsius, times the specific heat. And again, you guys, because this is aqueous, we're going to use that specific heat of water, which is 4.18 joules over grams degrees Celsius. And let's go ahead with the boop. Let's go ahead and plug this all in. So I've got 1,250 grams times 5.3, and that's a negative degrees Celsius, times 4.18 joules over grams degrees Celsius, equals a Q for acetic acid. And there it is. Q is, I remembered, it's acetic acid is CH3, and then OH, CH3OOH. And if I do that, I get a Q of, what is that, negative 27,692.5 joules of energy. And again, you guys, I can cancel out my temperature unit of degrees Celsius. I can cancel out grams, and I'm left with this unit, joules, which is a unit of energy. Now, recall, though, that we are trying to find the delta H of this substance right here, the NaHCO3. And as a result of that, what this means right now is that the acetic acid is losing 27,692.5 joules of energy to the NaHCO3. So if this is losing it, it means the NaHCO3, it's gaining it. So that's going to make this a positive 27,692.5 joules. So this is the quantity that we're going to use in order to calculate the delta H of the substance NaHCO3. So the delta H for this substance, NaHCO3, equals the Q, or the change in thermal energy. the NaHCO3 over the moles of that. So what that means is our delta H is going to be equal to this quantity, positive 27,692.5 joules over, and I'm going to use that quantity right there for my moles down at the bottom, 0.1433 moles. And if I do the math on that, my delta H equals, let's go ahead and do the math on that. So I've got 27,692.5 divided by 0.1433 equals the change in, or the delta H is 193,248.43 joules per mole of the NaHCO3. So now we're asking ourselves, is this process endothermic or exothermic? So essentially what happens is we have a calorimeter that's filled with acetic acid. We drop in 0.1433 moles of this substance right here. And what happens is that this substance gains energy. So this substance absorbs energy while our acetic acid loses energy. So as far as breaking this up right here, so breaking up my base right here, this is going to be, because this number is positive, this is going to be an endothermic process. Okay? Because remember, you guys, when it comes to these processes, we're essentially dealing with what's happening in the surroundings. In this case, the surroundings is the acetic acid. The acetic acid, you guys, is losing energy. This is gaining energy, so it's overall, the overall energy change in this is endothermic. The overall energy process for the acetic acid is actually exothermic because it's losing energy. But again, we're talking specifically about this substance. So for this substance, the overall change means it's an endothermic process. Whew, lots going on here. So like I said, you guys, when it comes to calculating delta H, there's a couple of things you have to remember. Delta H, you guys, has to do with the energy that's being absorbed or lost in the reaction itself, not in the surrounding substance. Okay, so that's a big difference. With Q, you guys, it's when we're finding the Q of something, we're finding the change in specifically heat energy of the surrounding substances or the surrounding system. And so we look at it a little bit differently. This we can measure. We can use temperature, something measurable, temperature, in order to calculate this number. Because remember, you guys, we can't measure enthalpy. We have to calculate it using what we would call indirect evidence. And the indirect evidence is what's happening with the temperature of the substances themselves. So once we know the temperatures, then we can calculate, and there's not like some enthalpy thermometer out there. There's no delta H thermometer that we can just stick into a substance and go, oh yeah, that's the enthalpy. What we can do is we can put a thermometer in certain surrounding substances, and we can gauge the temperature, and then we can use the temperature and how much of it there is and its specific heat, so how much energy it takes to heat 1 gram of that substance 1 degree Celsius, and then we can eventually calculate our change in enthalpy for the reaction itself. Okay, a lot going on there. Good luck.